after Dan talks, but I'm extremely happy to get a little part of the Spring community here and to talk about WebAssembly and what I think is the future of the JVM ecosystem and how things will evolve in the future. So this is my very, very first Spring I/O. Great energy, great vibe. Thank you so much for having me, and thanks so much to Sergi for organizing such an amazing conference. Thank you, everyone. So let's talk about me, because I'm not very much part of the Spring community, so far, at least, and I want to spend a couple of words. I'm Andrea Peruffo. I'm a principal software developer at IBM. I'm actually Italian, but I live in Lisbon, and it's like more than 20 years that I'm doing this job now. So I started with embedded systems, worked on PLCs and industrial machines. I went to work for banks, telecommunication companies, distributed systems, startups, many different kind of industries. And I did a lot of Java meanwhile, and a lot of things on the JVM as well. We have a super packed agenda for today, and since I'm the one in between you and your beer next, we will have a burning surprise by the end, so that you have to stay awake and hopefully follow me in this journey on WebAssembly, and we will have a great announcement by the end. So we will go through a little bit of a WebAssembly intro. How many of you don't know nothing about WebAssembly? So this is very much good for you. And we will go through a few use cases that will show how WebAssembly is useful today on the JVM for your applications. We will zoom on Chicory, which is the project I'm mostly working on. We will have this burning surprise, and we will go through conclusions. So what is WebAssembly? Just Wikipedia definition. WebAssembly defines a portable binary code format and for executable programs. But this is not the entire definition. The entire definition states that it also defines very well the interactions in between the WebAssembly module and its host system. So how you call a function in the WebAssembly module and how you expose your host system inside the WebAssembly module. So the two ways on how WebAssembly can interact with this host system. So from the very definition, you can see that it is very much toward embedding, not running standalone application, but it has been defined and implemented to be a specification for programs that will be embedded in other programs. And binary format is easy because it goes very well machine to machines. It's compact. Machines understand very well binary. We don't, so there is a corresponding text format to help people understand what is going on in the program. Why WebAssembly born in first place? WebAssembly born for the web platform, born for the browsers, and for speed. Because what happened is that in the browser, the language that you have available is JavaScript. JavaScript is a dynamic programming language. You cannot get high speed, and you cannot run CPU-intensive tasks on it efficiently. So you have limitations on how you can run a renderer or some CPU-intensive tasks in your browser and in your client-side applications. They wanted to overcome this limitation, and from the initial experiments of ASM.js, if you are familiar with it, they went down the path of standardizing with W3C, a specification of WebAssembly that enable system programming languages like Rust, C, C++, Go, to be compiled to WebAssembly and run at near native speed in the browser. So once you can write a C renderer and you can run it safely in the browser, you have the speed, and you can compose much better apps for your user, much nicer. So even if you don't know nothing about WebAssembly, you are using it every day because it is actually powering like a Google Maps, all the Google Docs, Excel, all the Google Suite, and many other products like Figma, Adobe, and other major players are putting it in production and is running in your browsers probably every day. Being in the browser space, you want those things to be very secure. You cannot run something that touches the memory in your browser that will corrupt all the client's machines that are running a browser. You want it to be sandboxed and very secure. What does it mean to go to take WebAssembly and bring it to the server side? It means that you get polyglot capabilities. So a lot of languages can compile to WebAssembly, and you will be able to just reuse them on the server side. Is easily embeddable. There are a lot of different runtimes for running WebAssembly, and you can actually hook them up and in many different programming languages and just execute them. Is extremely portable. Is again one thing is portable across operating system and architecture. You have one single target, which is WebAssembly, and you don't have any more ARM, x86, or Windows and Linux differences. And is secure, as I told you, is designed to run untrusted code, to run code that you don't want to trust that comes from different users. And again, it's part of W3C. Why I'm stressing it? Because a lot more applications are making use in the browsers of WebAssembly, and more things are becoming compatible with WebAssembly, and we just want to be able to reuse those things on the JVM or on any other server-side component, because it's extremely convenient. When we talk about WebAssembly, we always talk about those two things. So there are a lot of different languages that can target and can compile to WebAssembly bytecode, and then you have the runtimes. So you take WebAssembly bytecode and you execute it. At the top, you can see V8, which is the engine that powers Chrome, or SpiderMonkey for Firefox, etc. And there are many others, like Ingo Was0 and Rust Wasm. When we talk about the JVM, we have a problem on running actually native code. So you can take one of those engines like V8 and just hook it up on the JVM, but it doesn't provide you the same ergonomy of a pure Java application. It makes, anyway, your application dependent on the platform it will run. You need to cross-compile your native piece of code for different operating system and architecture and distribute the native library to be able to actually run it. And during runtime, the execution leaves the safety and observability of the JVM, which means you lose all the debugging capabilities, you lose all the monitoring, you lose all the debugging tools that you're used to use, and especially when a bug happens or a problem happens in the native code, in the native side of the code, your JVM simply crashes, which is something that you don't want to happen. Instead, when you stay within the JVM boundaries, you have a lot of guarantees, you have a lot of things. So you have memory safety, you can configure the memory, the garbage collector, etc. of the JVM very, very precisely. You have a fault isolation, so if something bad happens in the native part of your code, in the WebAssembly payload, you will get an exception, not a JVM crash, which is very different. And you have advanced just-in-time compilation, which means that your WebAssembly module will be optimized during execution to run faster and faster, execution after execution, like a normal Java program. Those programs are self-contained. You can just distribute a jar, and the jar will just automatically run on any JVM wherever you deploy it, and is easy to run in regulated environments. So you are running probably Spring Boot application in regulated environments, and shipping WebAssembly payload will be just adding a library, adding a dependency to your project, so it's exactly the same. And again, we are back to write once and run everywhere that comes from the JVM. That was the promise with applets, etc. But this is finally secure. So probably we get much closer. So again, what does this mean to you Java developers? This means that you have all those fantastic programming languages and then a lot of fantastic applications written in them, and there is magic. And we can finally execute it. Let's start with the very first example where this approach shines, and this is probably the angle that reasons the most with the people I talk to. We talk about JavaScript specifically. The situation on the JVM with JavaScript is kind of bad in the sense that you have two deprecated engines, which are Rhino and Nessorn, which are deprecated, barely maintained, often with CVs and problems that takes time to resolve, etc. And on the other side, if you're lucky enough to run on GraalVM, you have GraalJS, which is actually a very good engine. But you need to be on GraalVM to squeeze all the performance out of it. So what happened? That it exists a very, very great runtime for engine for JavaScript, which is called QuickJS. QuickJS is a C engine, which is very small, but it is already compatible with most of the ECMAScript specification. So it's able to actually run basically any JavaScript program. And it's done for embedding, which means that it doesn't have the node or browser APIs built in, but all the rest of the JavaScript can just freely run. And you can expose more functionality on top of it. So we take this C engine that someone written, and that is very efficient, very small, very portable, and we wrap it with our QuickJS. Why Rust? The Rust toolchain is great for emitting WebAssembly modules. So the Rust toolchain is much superior than any other toolchain that exists right now. So it's very convenient if you want to compile something to WebAssembly, to wrap it into a Rust container and go on from there. And then, thanks to Shopify, that is running this stack in production to enable you to have custom actions on top of their on their shops. We have Javi, which makes our QuickJS even more kind to be run in WebAssembly. So they specifically have a wrapper for our QuickJS for targeting the WebAssembly target and making it very convenient to be run. What happened is that, again, we want to run all of this with Java. And what I did is to take this amazing stack that was already available and wrap it into a pure Java application. So what this does mean is that you don't want to see all this complexity. But what you want to see is just a single jar that you download is about, I think they just checked is like 700 kilobytes of jar that fully contains a full-fledged JavaScript engine that I haven't written. I have just did the binding to work the JVM, and you can import it very, very easily. For example, with JBang is just one line, and this is fantastic Java 26 that enabled me to squeeze a lot of code in a very little place. So you can actually run JavaScript inside your Java application very, very easily, just adding a dependency and using it. The runner will be completely safe as the heap space is separated from your host space, and this is completely dynamic. So this means that you can run any JavaScript payload, even if your application was compiled with native image in first place. So we restore the dynamic capability of the JVM by enabling native payloads to be run again. And by chance, so there is this project called Microcks. There is a workshop about it happening in the meantime. And the Microcks is a great CNCF project, which enables you to do API mocking, basically. Serve API mocked for your application. You provide OpenAPI, FastAPI, whatever, and you can return mocked response. By chance, Microcks is a Spring Boot application. But it's part of the CNCF, and they used to enable their people to customize those mocked answers, those mocked responses, using a Groovy dispatcher. You can imagine what will be the reaction of someone working on Kubernetes and having to write Groovy. They want to write Go, they want to write Python, or maybe JavaScript, but they really don't want to touch the JVM from even with a stick. So I went there, and they were looking for options to run a different programming language, to write those dispatchers, and I integrated QuickJS for J. Integration went smooth, and now they have a JavaScript dispatcher that enable you to write those little snippets of JavaScript code that will be executed in the JavaScript in QuickJS at the end of the day, and all of this is fully compatible even with native image. So you can take Microcks, compile it to native image, run it efficiently, fully statically compiled, and still execute dynamic payload and JavaScript on top of it, which is a great power. And if you want, this is a link to the project, QuickJS. Yes, is available offline later, no worries. Yeah. So next, let's talk about Open Policy Agent. If you haven't heard about it, it's another CNCF project. OPA is a policy engine, so it enables you to run policies. This is often used for authorization on top of Kubernetes, and for running authorization payload or validation or doing those kind of job on top of Kubernetes platform. They let you write those policies by using a language, which is a data log language called Rigo. And this is an example, a very, very basic hello world example that will allow no one but Bob to access something or to do something. And what happened is that all the stack of OPA is written in Go, and this is the integration they offer you or they suggest you in a classic way. So you have a request or an event or something that goes into your service. Your service does an HTTP call to an external OPA server and gets the response if it can go on or not based on the policy or the Rigo file that you loaded there. But what happened is that they designed it in a very smooth way, so that OPA build, you can actually compile this data log language directly to WebAssembly and execute it in WebAssembly. What does this mean for you? That you basically just cut the network call. So you don't have anymore to go out and check your policy against an external third-party system. You just run it in process. This is much faster, convenient, less infrastructure to maintain, more practical even to implement and use into your services. As an example, since we are at Spring.io, I took a Spring Cloud Gateway and I wrote a filter for it. And as you can see, it fits as the full implementation fits a slide. This means that you can take an OPA policy, load it dynamically when you receive a request, and execute it and evaluate it on the user input. In this case, I'm getting an header just for demo purposes and understanding. So if you put Spring Cloud Gateway in front of your application and you want to do authorization, this is a very easy integration that you can do. And yeah, I have a little demo. You can, it's not that fancy, so it's just a GIF. And if you are the user Alice, of course, you will receive back 401 because your access is forbidden. But if your user is actually Bob, the one that that is allowed to access your service, you receive 200 back with the things that got filtered. This repository, Spring Cloud Gateway Wasm demos, comes from all the demos done for Spring Cloud with WebAssembly, and it contains a bunch of examples running JavaScript, C, JQ, or OPA, many different things, just for you to see how this integrates with a real-world project like a Cloud Gateway, or how you can leverage it. Next, we talk about Protobuf. For sure, you have heard about Protobuf. Is widely used nowadays, and what's the deal with it? So my Quarkus, I work next desk to people developing Quarkus, and they came to me and said, okay, we have a problem with Proto-C. So Proto-C is used to generate the code that you will be using at runtime to conduct different services. So with Proto-C, which is a C program, CLI, you generate the Java code that you will be using. What happened is that with Quarkus gRPC, they attempted to make the user experience really smooth. And to make the user experience really smooth, what you do is just you pack all the binary that are available, and you make them a dependency, a transitive dependency of your generator. And this means that just at compile time, which is not a huge problem in a lot of context, but this piles up to compile dependencies that are up to 400 megs, which for an hello world, which seems a bit excessive, if you want. And they came to me and say, can you do anything about it? So again, old story new, we took Proto-C, we compile it for WebAssembly, we wrap it as a pure Java library, and the full Proto-C functionality is available in 1.3 megabytes. So for all the architecture, because it runs as pure Java bytecode, you don't have to target any more different specific architecture, and you can just run what you need on the JVM as you're used to. And compile time dependencies went down to 90 megs, which means that we spared like 300 megs just by using these kind of things. And the result of Proto-C is byte by byte the same as the native application. So I haven't rewritten Proto-C. I haven't, like they did at Square with Wire and those other libraries. I've just recompiled Proto-C in a WebAssembly payload and make it able to be shipped on top of the JVM. Those are the two projects. If you want, I have done this for the integration of Quarkus gRPC 0, but all the engine is available in Protobuf 4J, which is the base library to expose these functionalities. Please be my guest to write a Spring extension for it. Next, we talk about code highlighting. So no one wants to see code in black and white, right? You want to have at least syntax highlighting when looking at a piece of code. You don't. It's boring, but it's not understandable if you don't have some colors of it. And you will tell me, Java is a server-side application. I don't need to show this kind of code. And well, it depends. So I have a friend, which is Max, the creator of JBank, for example, that started to work on this project called, sorry for my bad French pronunciation, but it would be Tambouille, or something like, and that enable you to write a terminal user interfaces in Java in the same way as Ratatouille and other things. This makes it for very, very fun and entertaining CLIs and terminal applications. And often, when you write a terminal UI, you want to show the code that is inside some files. And you want syntax highlighting. So the problem comes back to us. What's the problem with it? If you look at Java, the landscape, I looked around and I couldn't really find nothing. There is something very, very little done in Eclipse, in some old projects done with regex, but is hidden inside some framework or Eclipse or the IDE or whatever. So there is really nothing. But this is a solved problem. we don't have to go through it again and again. Code highlighting is a solved problem, and for example, you have those two things that comes up to mind immediately. The first one being highlight.js, which is a JavaScript library, again with regular expression, but that enables you to do syntax highlighting in the browser. And the other option is called three-seater. Is a C and Rust library that enables you to write grammars, and is basically the engine that is used behind VS Code, for example. So all the syntax highlighting done in VS Code is done through three-seater grammars. We have WebAssembly. Who can stop us? So you can write highlight.js on QuickJS that I presented before. So this works out of the box, but I wanted to squeeze a little more performance out of it. So I went for, I did a POC of running highlight.js just to show that it was possible, but I took the way of integrating three-seater. And I found a library that is wrapping three-seater grammars and making them available with a lot of different themes. And this is called Lumis. It's a great project, and enables you to do syntax highlighting for like 70 more languages and with a lot of available themes. And as you can see, the API that you will use to use it is super easy and super simple, and enable you to do some very, very cool demos, finally with some fancy colors and showing the code in very different things. Again, the Lumis 4J was done probably in less than a day, the initial version. So it takes very, very little to just wrap the work of other engineers and all the effort that they put in it. This is a link to Lumis 4J if you have any use case for it, or you want to write your own terminal UI with fancy colors for your programming language. And there are a lot more stuff. So we started from databases. So we have SQLite running as a pure Java dependency. We have JQ, the command line tool that you use to parse JSON, etc. We have even ported Postgres recently. So we have PGLite, which is a port of Postgres for the browser, which is running as pure Java. Again and again, Prism, a Ruby parser, Bazel, the build tool from Google. OpenFeature is using WebAssembly to ship the logic of feature flag in different SDKs in different languages. We can run CPython. We have Go single message transformation in Division and much more. So you are missing. Come. And what makes this possible is Chicory. So let's zoom in. And what is Chicory? Is a WebAssembly runtime written in Java for Java. The alternative on the JVM will be Graal Wasm. And what does it mean for you? It means that all this magic is provided to you thanks to Chicory. Chicory started in 2023, thanks to Benjamin Eckel, at the time CTO of Dylipso. And I joined the effort like 1 week after he started. And in 2023, we developed basically all the basic part of an interpreter for WebAssembly. So you can run WebAssembly interpreted on the JVM. We realized that this was useful and very cool. But in 2024, we went over and developed a compiler for WebAssembly. If you look at WebAssembly from far enough, WebAssembly bytecode looks very, very similar to Java bytecode. So we are almost translating one-to-one WebAssembly bytecode to Java bytecode to be run directly and natively on the JVM. We got it running. In 2025, we focused on getting more proposals and more specification compliance on this engine, and we did a lot of applications, and some of them are the one that I presented before. In 2026, we integrated Wasm GC, which is a big chunk of proposal that enabled more languages on top of Chicory, languages like Dart, Kotlin, or even Java. And we developed more libraries on top of it. how Chicory is a little, as I was saying, Chicory is a little different than a normal compiler in the sense that it doesn't produce a machine-specific assembly, but it produces Java bytecode, which is self-contained, fully secure, fully portable, just a plain jar, and there's a very nice side effect. Everything that runs outside, everything that gets generated out of the Chicory compiler runs even on Android. We have been told that, running WebAssembly on Android, the easiest way to do it is using Chicory. We have covered a lot of the proposal. We have the core WebAssembly. We have threads, which is not in the spec just yet, but is still a proposal. We have multi-memory, Wasm preview 1, WasGC. We need to finish some details to run it even faster and better on the JVM, but the full API specification is fulfilled, so you can actually run stuff on it. So if you are not aware, on the GraalVM team, they did something extremely interesting, and they took native image and made it able to emit WebAssembly bytecode. And they called it GraalVM web image. So you can take Java bytecode, compile it with GraalVM web image, and emit WebAssembly. Now, you can take this WebAssembly, take Chicory, compile it back to Java bytecode. And you can go on and on. Getting some slowdown because of various things, but this works. More interestingly, what happened is that, for example, you can get a Rust payload, compile it with Chicory to run on Java, and then you have a Java application that will run on the JVM on one side, and maybe in the browser or on Node, and you can compile it with web image and get the same thing to run through Chicory in web image in your final application. This opens a lot of things. It's not maybe useful for the end user, but it helped me to find like bugs in this integration, and now this integration fully works. When we look at performance, you can see that Chicory is quite good. We started comparing it with other runtimes. Wasm, which is a Rust runtime for WebAssembly, and Was0, which is written in Go. And you can see that performance are very, very close in most cases. In some cases, like in Fibonacci, the JVM seems to be very efficient at inlining loops, so is even more efficient than other implementations. Yeah, and Chicory is a community project, so please come join us. We recently reached more than 1,000 stars, which means a lot for a Java project at least. Maybe not in other ecosystems, but well, that's where we are, and we are open to contributors. Please come and join. And link to Chicory, please come and start a conversation with us. So, now, we did all of this. We believe we deliver some value, and we started to receive feedback by the user. And guess what was the biggest complaint of users? So the biggest complaint was the sandbox to you, so everything runs really isolated. No one cares about the sandbox at the end of the day. What people want is just raw speed. We realized that a lot of people come to the project and they forget about all this first part about safety, running things smoothly and nicely on the JVM. They just want raw speed to run the payload. That's what they want. And the problem is not something that is easily solvable by us staying on the JVM. This is JDK 11, but there is this thing called a huge method limit, which is set to 8,000 since ever, I guess. And this means that when your function or method exceed 8,000 bytes of size, it will never be compiled by C1 or C2 or any just-in-time compiler on the JVM. So this means that as soon as your function or method goes a little above this size, it will run in interpreted mode. And in interpreted mode is very slow. You take orders of magnitude of performance penalty compared to any compiled alternative. So if you are not very if you don't take a lot of care when you write your Java code, you will have very bad performance just because the JVM will not even attempt to optimize it. So what happened is that for us, that we are writing a compiler from WebAssembly to Java, we cannot really change the size of the functions because those are user input for us. It's not something that we can refactor or easily do something different. So what happened is that I started writing Redline, which is a new compiler for WebAssembly. And this time, as you can see, is hot and there is fire because we need to go a little bit unsafe to squeeze every performance byte out of it. And Redline builds on the very foundation of Wasm, which is the reference implementation of a Wasm runtime written in Rust. The compiler that stays behind the Wasm is called the crane lift. And what crane lift does is it takes WebAssembly and emits assembly-specific code. Again, we are back to the problem that we have x86, ARM, etc., Linux, Windows, but we have a compiler that does it for us. This compiler is written in Rust, and guess what? We can run it through WebAssembly. So we compile the compiler written in Rust to WebAssembly so that it can run natively on the JVM, and we have our compile time toolchain fully accessible on any JVM. Once we have this assembly, we cross-compile it for like 6 different combinations of architecture and operating system, which are the most common, and we bundle it in the jar along with the Chicory version. So if you are on a supported architecture, you will get all the speed. If you are not on a supported architecture, you will get Chicory, which is anyway very fast, and will run anywhere the JVM will go. But once we have a jar, what happens is that there is a little bridge of magic, which is done with Panama on Java 25+. And we have a fallback using JFFI, which uses JNI behind the scenes. But it's just a fallback for retrocompatibility if you can't use Java 25. But with Java 25+, you still don't have any dependency. So you can run WebAssembly with 0 dependencies on the JVM thanks to this. And the last bit of the equation is mmap. So with Panama, what we do is, if you are not familiar with mmap, basically you are reserving an area of your memory, you are dropping their assembly code, and say to the machine, OK, just execute it. This is unsafe, as you can imagine. This is native access, but this relies only on libc, standard library. So this is available on any machine, and this runs really fast. So we took again our benchmarks, rerun them, and as you can see, the numbers are very close or even better than other runtimes. So we are in the same order of magnitude. Again, don't take those numbers as something big. They are being run on GitHub Actions, which are noisy, etc. So we are doing good. And I can share even more. And we have been running more payloads, and we got a lot of much speed up, especially on some applications. And this is Chicory Redline, and this is the very first time I'm showing it out in public, and I'm very happy of it. Yeah, check it out. Yes, conclusions. We don't want to rewrite our applications. It doesn't make sense that you rewrite JQ for the JVM just to have the same semantics of the language that parses JSON. It doesn't make much sense that you rewrite SQLite in Java to have a database. You don't want to rewrite those things. You want to reuse everything. On the JVM, The JVM is a perfectly viable runtime that enables you to run things safely and fast when you want, and depending on the trade-off that you have, you can take your party and you can decide how to run those things. So you can happily just merge and take different languages, compile them to WebAssembly or run them on top of the JVM, and you will have one runtime to run any different language without a trouble. What I see coming is that WebAssembly is not a hype technology that you will see along with AI and whatever, but it's something that is spreading. This is happening in the browser. Most NPM packages are containing WebAssembly as of today. The same will happen on the JVM slowly and steadily. So you will have WebAssembly payload hiding behind Java APIs that access the functionality. You don't need to write a Rust program that brings you a functionality that is useful for business or that is useful for your application. You can just embed it, ship it, and run it from full Java application. And thank you, everyone. We have 5 minutes to take questions, if there is any. Oh. Yes. Yes, yes, yes. So it very much, can you hear me? Oh, okay, sorry. It very much depends on the pay. I think this is not working. Anyway, yes, we did it. It very, very much depends on the kind of workload that you have, unfortunately. So this very much depends on what your program is doing behind the scenes. But in general, WebAssembly promises near native performance, and we can get to run usually payloads in the order of magnitude of 1x, 2x the native one. Yes, it's working again. Apart from that, you have some payloads that pay more a higher price on top of the JVM. For example, when you have a big parser, like the SQLite parser for queries or the CPython interpreter, like those huge functions that you can that are very, very hard to split or break. There you pay an higher cost running purely on the JVM. And that's why I developed a Redline that will bring back the near-native performance even to those payloads. And we have been seeing very, very good numbers on the real-world payloads running on it so far. I hope this answers. Good? Thank you so much for being here.